So we spent the first couple of weeks modeling continuous outcomes, and we're now just transitioning into binary logistic HLM, where we will be able to model dichotomous outcomes. This is very similar to the difference between OLS regression and binary logistic regression, but there are slight differences because we now have clustering, but I'll walk you through this. So I want to do a quick logistic regression review. Logistic regression models a dichotomous dependent variable and relates explanatory variables. In comparison to that, we have the same kind of idea that we have covariates to dichotomous dependent variable, and the observations are nested. We can have clustering the same way we have it in what we've done before. So we have participants within clusters or any kind of units within clusters. Or we can have longitudinal data where we have repeated observations within subjects. And we're going to get to that later in the course. But that would, for example, be HIV positive or not over time. So it's a 1-0 coding with data over time. I want to talk through a logistic regression example. This one is from Hedeker. It is the simplest example that we can think about, and it is the simplest because we have our predictor X is dichotomous as well as the outcome. So assuming that 1 is a positive response and 0 is a non-response, in this case, we have 90 people in the control group and 90 people in the treatment group. We can add the cells easily. That means we have 180 people in this experiment. And as you can see that after the experiment in the control group, we have 60 people at 0 and 30 people who had a positive response. Now in the treatment group, the ratio is exactly the opposite. So we got 30 people at 0 and 60 people at 1. What does that mean? We can now talk about this in different mathematical terms. In the control group, the probability of having a positive response is 1 in 3, 30 out of the 90 in the group. So we have a probability of a third. The treatment group is 60 out of 90, which is 2/3. So we have the probability of being in a positive response at the end is twice as high in the treatment group as in the control group. Now, what are my odds of being in the response group? So the odds in the control group are 1 to 2. And in the treatment group, it's 2 to 1 or 2. Now, the logit for these situations can be calculated, and it's negative 0.693 for the control group, and it's positive 693 for the intervention group. And I'll walk you through these kind of things. So if we're looking at the logit, now the logit is of the probability here, is the probability of being in group 1, of being a success, divided by not being success, which is 1 minus 1, having success. The reason why we do this 1 minus 1 thing is because we could have more groups when we get to ordinal logistic regression or multinomial regression. So it's the event over the non-event that we want to look at. And on the right-hand side, we see the regular regression expression. We have a beta 0, our intercept, plus beta 1 times x. And now this gets an I as an index, which it kind of always has, but we don't put those into regression because all we have are individuals. So this is our level 1 or only level logistic regression formula. The logit of these probability is equal to a regular regression on the right side. So let's continue. There's some formulas down here, and they will lead to more meaningful things on the next slide. But if I want to calculate the exponent of beta 0, these are the odds of the response for x being 0. If x is 0, then the beta 1 times x becomes 0. So what are the odds that I end up in group 0, and we know that this is the that we have a half. The odds are a half. We figured that out earlier up in the table. Now, if we have the exponent of beta 0 being a half, then to get beta 0, or in this case the expected beta 0, we need to take the logarithm, and this is the natural logarithm, and we get the negative 0.693 that we have up there in the table. Now, what if we want to know what's the other case? What if we're in group 1? Group 1, the odds of being in group 1 we know is 2. So we know that the odds of being in group 1 is equal to the logarithm of 2. And we get the 0.693. Now this is beta 0 plus beta 1. So if I want to know how much beta 1 is, I have to subtract beta 0, which gets us to 0.693 minus minus or plus 0.693, which is 1.386. So this is how we can get out of this formula the individual pieces of odds for a specific response. So there's some more math here for those who are interested in the steps, but what it comes down to is that the odds ratio is the ratio of the odds per unit change in X. In our case, the odds ratio for the intervention is the ratio of the odds for being in the intervention group compared to the control group. And if you do a little bit of math and know a little bit about how exponents work, then you will see that the odds ratio for the response here is the exponent of the 1.386 that we calculated before, and that is 4. So the odds of the response are 4 times higher in the treatment group relative to the control group. And that's a large odds ratio. Also note I added a reference to an article by Chen in 2010 about odds ratio sizes. Sometimes people ask about it. Cohen's talking about effect sizes in terms of Cohen's d and other things. There's an interesting article here that if you're interested in how to talk about odds ratios in terms of small, medium, and large, there's some language and some suggestions in this article. So you might faintly remember this is a representation of how probability behaves when we're talking about logistic regression. As you can see that this is not linear. Now between 0 and 1 this looks fairly linear, but it causes some problems. So we're going to use something different that's on the next slide. So this is the mathematical magic that's happening given that the probability has this S-shaped curve, and depending on what you're looking at can be a little bit more squished, can be a little bit more extreme. The logic turns this mathematically into a linear relationship. That's what we're used from the OLS regression and the regular HLM, that we have a linear relationship. So what this now means is that we have a link function, and in our case we're going to use a logit link function that links the outcome to a linear relationship with the predictors. So there's a general structure to all HLM models that we haven't talked about because some things were just simple right now. So the two things we haven't talked about are the first two bullets on this slide. We haven't talked about a sampling model, and we just started talking about a link function. So if we have a normal distribution, that's our sampling model, and that's the easy one mathematically. And for that sampling model, the link function is the equality, meaning there's just an equal sign. So the left-hand side of the equation is equal to the right-hand side. Now I will talk about the sampling model for the binary logistic HLM and or regression on the next slide, but we have a different sampling model, and therefore we need this logit as a link function. And then we have what we call the structural level models, and those are the predictor models, and they are identical across all models. So on your right hand side, after you've identified your sampling model and your link function, everything looks the same. And this doesn't matter if you have a normally distributed continuous outcome, if you have a dichotomous outcome, if you have a multinomial, a ordinal, a Poisson distribution, a zero-inflated Poisson distribution, or anything you might come up with, that's been being dealt with in terms of understanding the sampling model and choosing the right link function. After that, everything else is the same across the multi-level models. I want to talk briefly about something that you should have been exposed to at some point in time, and that's the logistic regression sampling model. And it's a Bernoulli distribution. You might have talked about a binomial distribution in class. I know some students have this in class right now. The Bernoulli distribution is a special case of the binomial distribution, and it's really the only one that we will be dealing with here. And so what that means is that if x equals 0, your probability is 1 minus the sampling probability, and if x equals 1, then you have the probability of p. On average in the sample, the mean is p, and the variance is p times 1 minus p. So this is a distinct variance of this model. We will talk about this later, but the variance is actually fixed to pi squared over 3. So we can talk about this. But p is the probability of success. So there's either success or there's not success. There is a probability assigned to success, and therefore there's automatically a probability to failure, which is 1 minus p. So if we have an experiment where the probability of having a successful outcome is 60%, then the probability of failure is 40%. There are a few more formulas, and those are also background information for those who want to dive deeper into these things. We will get to applications shortly, and then it is not as complex and complicated anymore. So for those of you who are now like seeing weird things floating on the screen, just bear with me, and over time this will be useful to some degree. So the Bernoulli distribution for the HLM sampling model I put out here looks pretty much the same when you start comparing them to the one on the slide before. There's a little difference in symbols. We have, instead of a P, we have a phi in here. And we have now two indices, assuming a two-level model. Your Y is a Yij. Technically before it would have been a Yi, but as I mentioned, in regression we don't note this because there is no second level. The mean or the expected value is the probability, the phi ij. It's the probability of success. The variance again is the phi times 1 minus phi. So it's just different symbols. It's the same idea, and we know that the clustering structure is a little bit more difficult, and so things are going to be more difficult mathematically, but luckily we don't have to worry about this because the software will handle that for us. What we need though is we need to know about the link function and we need to know about odds. So Nij is the log odds of success, and that's defined just the way we had it before, not a p but a phi. And then the odds of y being 1 is also defined the same way. It is defined as Enij, eta ij. So if we have the regular equations, all we have to do is take the exponent to get the odds. Again, this is the mathematical background, so no need to worry if this is right now over here. Now this is the level 1 structural model. And now this looks familiar again, except on the left hand, instead of having a y, we have this eta, which is the logit of the y. But on the right-hand side, this is your regular level 1 model, beta 0j plus beta 1j, x 1ij, and so forth. So now that we've dealt with the link function and the model distribution, the sampling model, we're back to the same thing. Now there's one thing that needs to be noted. There is no error term. In logistic regression, this is not just logistic HLM, coefficients and error variance cannot be estimated both. So in these models, the error variance is fixed to pi squared over 3, which comes to about 3.29. So that is important. Why? A, you won't get an estimate. B, if you want to calculate an ICC, you need a level 1 variance. So the ICC formula gets simplified. And all you need then is your tau 0, 0. And as you can see below, all you do then is you plug in 3.29 for your level 1 variance, and that's how you can calculate your ICC. Don't forget about that because it is really puzzling if you look at the output and you can't find your level 1 variance and you need to calculate an ICC. We've covered 3-level models, and as I mentioned, you can have more than 3-level models. And the higher level structures are exactly identical to those who are not in logistic models. As I mentioned before, they will look exactly the same way. You will have your beta 0J, and that will be defining your gammas, and you will make decisions about random and fixed effects. So on that end, nothing is different. The big difference is setting up the model correctly, and then, as I will be talking about next, interpreting your results correctly. So interpreting your results. For logistic HLM, you will get two sets of your results in HLM7. You will get unit-specific results and you will get population average results. Those use different assumptions about underlying distributions of the random effects. And this does not exist for normally distributed outcomes. This is a unique thing for your logistic HLM. We will, for the most part, be looking at the unit-specific model, and that's what the output will read. And it presents the coefficients for a hypothetical unit or a group where the random effect is 0. Within unit covariates, model unit-specific trends. So this is all about the units you're looking at. Fixed effects are conditional on the random effects. The research in these studies aims to investigate properties of individuals in the context of their units. That's important. If you have questions around peer influences, that's what you want to look at. If you have questions about a context-specific predictor, let's say a policy, that's where we're going to be interested. So we're interested in what's going on in terms of how do the clusters influence individual behaviors and relationships. Now, HLM gives you also the population average model or the GE model, which is something we haven't talked about. GE models are different, but in some aspects similar to HLM models. But the goal for these are population average results that can be deduced as characteristics of the distribution of the unit-specific results. They give answers to population average questions. So those are used if you are running multi-level models, but you want actually national representative population estimates. Most of our research is not interested in that, but I wanted to bring that up. And if you were running your analyses in a different software package, you would actually choose a GE model instead of a multi-level model. And so the idea is that we're now treating the variances due to the clusters differently, and we're talking about predictive probabilities for the population. And so the results are averaged over clusters rather than looking at the individual cluster effects. As I said, those are probably not of interest in most cases. Fixed effects in logistic HLM are interpreted exactly the way we interpret the betas in a regular logistic regression. And so if you have a positive gamma or positive slope, that is associated with an odds ratio that is greater than 1. And that indicates that higher odds of the outcome as the predictor increases. So with each unit increase, the odds ratio, the higher odds are higher by that factor. Now, why do I use the term factor? Because we're going to be multiplying. So odds are interpreted as a multiplicative change per unit increase. So if you have your x is 1, then you get the odds ratio. If your x is 2, then it is odds ratio squared because it's odds ratio times odds ratio. We will talk about this in class and in the applications in detail, but this is an important piece of information. So this is an overview slide that can help when you're writing things up. Now, you might already notice this when you're reading logistic regression findings that people talk about odds and that's it. But once in a while, you want to actually interpret these things for a lay community or people who are just not that familiar with what these odds ratios are. So if we're talking about the interpreting a gamma 0, 0, that's your odds when y equals 1 of y equals 1 when all predictors equal to 0. Remember, that's again important um, when we're looking at centering, so you might pay attention to that again. The gamma 0, 1, that's your level 1 predictor, your level 2 predictor, pardon me. And that's the multiplicative change in odds on average holding the other predictors constant per unit increase in W1. So this is a level 2 predictor impact. Similar interpretation is the gamma 1, 0, just in this case we have a level 1 predictor. But then when it comes to the interaction effect, which usually starts with a gamma 1, 1, we're talking about a multiplicative change in change. And on average, per unit increase in X, holding all the other predictors constant, of an increase by 1 unit in Y, holding other slope predictors constant. So that's a mouthful. But what you have to talk about now is a change in change. Again, we will be using this in class. So this is the hardcore introduction to logistic HLM. But as you will see, the interpretation is the hardest part of this entire thing.